Last time we defined the gradient, right, of a function, right, man?
Mm-hmm.
Gradient vector. Yeah. So let me recall it. What is gradient vector? So if you have a function, so let's say for the two variable, let's say if you have function of two variable, f of xy, g equal to f of xy. So it is a scalar valued function. So for every point xy, we have a scalar f of xy. Now you can immediately, at every point you can attach a vector, so that we call the gradient vector. We denote it by del f xy. So how it is defined? It is defined by the vector having component del f del x I cap plus del f del y j cap. So if you have a function of two variable, then the gradient vector of that function at the point xy is given by this vector del f del x I cap plus del f del y j cap. Okay, Mayan? Fine?
Yeah.
Right. So now if you have function of three variables, say f is a function of three variable x, y, g. So then we also can define the gradient of this function at a point x, y, g by the vector del f del x I cap plus del f del y j cap plus del f del z of k cap. It is defined this way. Now we'll see, this gradient vector has some geometrical meaning. Okay, last time I told you. So for example, for this, if you consider function of two variable, then geometrically, so for example, if you fixed a point, let's say we fixed a point p, a comma b is any point in the domain,
Mm-hmm.
yeah, domain of f function. So we take any point in the domain of the f function, and so then we get we get a level curve that is given by basically f of xy equals to f of a comma b, right? F of a comma b is a constant. So the relation between xy, you know, so we have a curve. So this is a curve in the xy plane, right? Right, Adhar? Right, man? So let's say we have this kind of curve here, right? And we take a point here on this curve. So it is the point p a comma b. Fine. Now see, we have a tangent plane at that point, right? So a tangent line basically, not plane. This is the tangent line. So the gradient will give you the normal vector. So like this. So the gradient of f at a comma b will give you the normal vector to the tangent line. Okay, Mayan, clear?
Yeah, fine.
Very good. So let me tell you here one example. Yeah. So here example. One second. So okay. Right. So so let's say here the question: sketch the level curve. Sketch the level curve to c equals to 0, corresponding level curve corresponding to c equals to 0 for the function. So for the function, let's say it is given by f of xy equals to y minus sin x. So we have a function of two variable f of xy. It is given by y minus sin x. Now find a normal vector. So now what should we do? All right. So 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 that the point p, the bracket, let's say pi comma 0 lies on the level curve, and find tangent line at p of pi comma at the point p having coordinate pi comma 0. Okay, Mayan, can you see the question?
Yeah, I can see it.
Okay, so let me read it again. Sketch the level curve corresponding to constant value c equal to 0 for the function f of xy equal to y minus sin x. So for your convenience, I can tell you, for a particular value, so let me take here c basically. So this kind of curve we call the level curve. So f of xy equal to some constant c. This kind of curve are the level curve. Now, if you take c equals to 0, then so let me write down here the solution. So what will be the level curve? So if I write here the solution, so the level curve will be basically f of xy equal to 0, because c equal to 0. Now what should we get? We get here y minus sin x equals to 0. So the level curve is basically y equal to sin x. Okay, fine.
Yeah.
All right. So this is the sine curve, right? So it is a periodic function. Now at the point pi comma 0, we calculate basically the equation of tangent line. So look at this. First we calculate gradient. So that gradient will be normal. So here I do that. So I think let me. So I'll explain this side here. I'll take this space, this much space for the previous, this one, this side I'm doing. Okay, here I'm doing the rest solution. So
Okay.
yeah, we have a sine curve. So basically, if you want, you can draw here the sine curve. Yeah. So at 0 you have 0, then like that. At pi you have 0, something like this. So you have the sine curve, right? So this way. So this is basically, you can say, the 0 here. No, so 0 mean at 0 it is 0, starting at 0. So this is here 0. So like that. So here 0, here pi, right? So let me take, instead of taking pi, let me put here pi by 2. then it will be better understanding geometrically. So pi by 2, if you put in the level curve in the place x, pi by 2, y, you get 1. So pi by 2 comma 1. Basically, I'm trying to tell you that how you can use the gradient of the function of two variable, you know, if you try to write down the equation of tangent line. So we are at the point here. So now the point we have pi by 2. So on the curve we have this point, say this is p, right? So we have the tangent line. Let me use the yellow color. So this is the tangent line, right?
Right.
Okay. So what should we do? We will write down the equation of this yellow line. So to write down the equation of yellow line, what we want? See, using the gradient, we will get a normal vector. So this way, we get the normal vector, right? So this is the gradient of the function f at the point pi by 2 comma 1, right? So if you calculate gradient of the function f at the point x comma y, what should we get? We get del f del x I cap plus, and this is geometrically give us the normal vector to the tangent line, right? So what is this? Del f del x mean what? Del f del x mean, you know, so if you take, so your function was basically y minus sine x. So if we take derivative with respect to x, we get minus cosine x, right? I cap, and then plus 1 of j cap, right? Fine, is clear?
Yeah, that's fine.
Okay, so
Perfect.
at the point pi by 2 comma 1, if you calculate, then what should we get? So x is pi by 2, so cosine pi by 2 is 0, so 0 of I cap plus 1 into j cap. So basically in the component form, it is of the form 0 comma 1 vector. So see exactly this vector, the this black vector here I have written, it is 0 comma 1. Although here, although 0 comma 1 up to this vector, but just we shifted parallelly at this point, this vector, right? So the unit vector along x-axis is shifted at this p point, right?
Yeah.
Ah, okay, fine. So this is the normal vector. So how you write down the equation of that, the tangent line? So you take any point on it. If you take any point, let's say q, so q is any point xy on tangent line, then what should we get? Then we get the pq vector. P already we know, it is the point given by pi by 2 comma 1. This is this vector from here to here. This is the pq vector. So this is your p point, right? So the pq vector is basically, so this is, so let me, yeah, this is your gradient. So this is gradient, yeah. So the pq vector is perpendicular to the gradient vector at the point pi by 2 comma 1, right? Mine is clear.
Yeah.
Okay, and
Yeah.
we know, yeah, pq vector is what? This is given by x comma y, and this is given by pi by 2 comma 1. So basically pq vector will be x minus, so this means x minus pi by 2 comma, y minus basically 1. This vector, if you take dot, you know 0 comma 1, so that will give you 0. So this is basically 0, right? Because these two vectors are perpendicular, so dot product will be 0. So if you simplify, you get 0 plus y minus 1 equal to 0. So this gives you y equal to 1. Okay, Mayan, this is the
Yeah.
equation of tangent line. Yes, see, if you have a curve y equal to fx, I mean y equal to sin x, this kind of curve, if you have, and they asked find the equation of tangent line at some point, So you can immediately calculate, just finding out dy dx, and that is the slope and point slope form. That way you can calculate. But here we are calculating the equation of tangent line using the gradient vector. Okay, Mayan?
Yeah.
Right. So they will give you a constant value and ask find the level curve and find the equation of tangent line at some given point. So what you will do basically, first you calculate the gradient of the function f at that point. So so that will be the normal vector to the tangent line. Now the rest work, what you do, basically you will take a point on the tangent line, then PQ. So let's say the new point you taking a Q having coordinate xy. Then PQ vector perpendicular to the gradient vector at the point P. So the dot product 0. From there you get the relation between xy. That is the equation of the tangent line to the level curve at that given point. Okay, Mayan?
Yeah.
Okay, this is
Fine.
for the this is for the two function of two variable. What happened if you have function of three variable? Now see, Now see, in this case, you will get the level surface, right, Mayan?
Yeah.
Level, yes, level surface. So level surface mean what? So the relation between x, y, g equal to some constant c. So this is a surface in R3, right?
Yeah.
Very good. So since once you have a surface, for example, you can take the sphere. The sphere equation we know x square. For example, if you take unit circle, y square plus g square equals to 1, right? This is sphere. This is the standard sphere. So something like this. Yeah. So this, right, man? This is a surface, right?
Yeah.
Yeah. So this is your f of xy, the function f of xyg, right? So let's say if you take any point here, let's say I'm taking the point P. Now at this point, we can consider the tangent plane, right? So a plane which touches the surface at the point P, that we call the tangent plane, right? So let's say this is called pi. Okay, Mayan?
Okay.
Right. So let P is any point on the level surface. P is any point. So let's say P is any point on the level surface having coordinate a comma b comma c. Let P a comma b comma c is any point on the level curve, sorry, level surface. Now I am using the term level surface. F of xyg equal to constant. So then the gradient of the function f at a comma b comma c, we know how it is defined. This is a vector. This is a vector, perpendicular, or you can say is a vector normal to the, you can say the normal to the tangent plane, or you can say the normal vector of the tangent plane. So is a vector normal to the tangent plane of the surface f of x y g equal to constant at the point a b c. Oh, sorry, I use the this notation. Let me put here d, because otherwise twice I'm using c. So this is, let's say, d. Okay. So this will give you, in this case, you will get a vector. The gradient will be a vector which is normal to the tangent plane. Mayan, is it clear?
Yeah, that's fine.
Okay. So what is the difference with the similarity with two variable? In the case of two variable, the gradient actually is normal to the tangent line, but for the the case of three variable, the gradient is normal to the tangent plane. So you know for a three variable case, we will calculate the equation of tangent plane, right? Also the tangent line we can calculate, right?
Correct.
Okay. So the gradient, yes. So the gradient vector is perpendicular to the tangent line. That is very important. A similar way you can say the gradient vector is parallel to the tangent, the normal line is parallel to normal line. Normal line at the point P of A, B, C to the level surface. So this is very important. So now we ready to solve one question. So did you understand the theory part, Mayan?
Mm.
Okay. I'm going to an example. So here it is. So find an equation of the tangent plane and normal line normal line to the normal line to the hyperboloid g square minus 2x square minus 2y square equals to 12 at the point 1 comma negative 1 comma 4. Okay, Mayan, this is the
Okay.
question, right? So let me read it again. So can you read it please, then it will be better for your understanding when I will write the solution. Can you read it?
Yeah. Find the
Okay.
equation of the tangent plane and normal line to the hyperboloid.
Hmm.
Z squared minus 2x squared minus 2y squared equals 12 at the point 1 comma negative 1 comma 4.
Exactly, yes, very good. So most of the time people, what the people do, that everything they bring, so the solution, so first you have to write down the function f. Okay.
Sure.
So this is your f function, right? Constant term you can forget, just take the all variable part, so that call f function, small f. So let f of x y g, if you consider this function g square minus 2x square minus 2y square, then we are basically working with the level surface f x y g equals to 12, right? This is the level surface, right, Mayan?
Yeah.
Okay. So just we consider this function. Now see what we are going to do. We are going to calculate the equation of tangent plane and normal line to this surface basically. So 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 first what you do, you will calculate the gradient vector of this, because it is a vector normal to the tangent plane at the given point, right?
Mm-hmm.
So del f del x I cap, yes. Del f very much easy. So these are very very easy. You can solve just using the gradient. We are now we are now observing the application of gradient vector. Okay.
Yeah.
Okay, so what is this? This is basically minus 4x I cap, then minus 4y j cap, and plus 2g of k cap, right? Just taking partial derivative of this expression with respect to x first. So from here we get only minus 4x, other two part are constant, so 0. So I put here minus 4x, then similarly minus 4y, then 2g, like that. Okay, Mayan?
Okay.
Very good. So now gradient of f at the point 1, negative 1, comma 4. So we are now replacing x by 1, y by negative 1, and g by 4. So if you replace it here, so you are taking x equal to 1, y equal to negative 1, and g equals to 4. So then what should we get? We'll get minus 4 of I, and then we get plus 4 of j, and plus 8 of k, right, Mayan? Is it okay, Mayan?
Right.
Okay, so you can say that you have a here, let's say this is the tangent plane at the point, let's say P, having coordinate 1, minus 1, 4. So now you have the normal line, so to the tangent plane. So the normal line is given by gradient of f1 minus 1, 4, right? Right, man?
Right.
Okay, now how we do this? So take a point Q, another point Q on the tangent plane. Any point, take Q on the tangent plane. So then the vector PQ is perpendicular, with the vector, the gradient vector at this point. So therefore, the dot product will be 0. And this is true for any point Q on the plane. If the Q point is outside on the plane, then this logic is not work, right?
Yeah.
Yeah. So therefore, this will give you the equation of tangent plane. So this is any point on tangent plane. This is any point plane, tangent plane at the point 1, negative 1, 4. The P point, let's say it is P. So then PQ vectors, one second. So then PQ vector, basically what you have seen here, that PQ vector is perpendicular to the gradient vector at the point 1, negative 1, 4. So what should we get? The PQ vector dot this equals to 0. Is it okay?
Yeah, that's fine.
Right. What is PQ vector? So this is x minus 1, y plus 1, g minus 4. This vector dot, the gradient vector is given by, so let me write in the component form. So this is negative 4, this is 4, 8. So if you put it here, then you get here negative 4, and then 4, then 8. So this equals to 0. If you simplify, you will get negative 4 into x minus 1 plus 4 into y plus 1 plus 8 into g minus 4 equals to 0. So you can factor out here 4, right? If you factor out 4, then minus of
Yeah.
x plus 1, yes, plus y plus 1, then plus 2g minus 8 equal to 0. Fine?
Fine.
Right. So if you simplify, what should we get? I'm writing so here directly. So you get minus x plus y plus 2g and minus 6 equal to 0. So this is, your equation of tangent plane of that hyperboloid at the point 1, negative 1, 4. Okay.
Okay.
Yeah, this is the tangent plane. Yes. So now let me write down. So now we will write down the equation of tangent line. So let me do it here. So this place I'm doing the rest part. Basically so normal line. So the normal. So it is very much easy. So write down. So so when we are talking about the line, so line will have three form, right? Vector equation, parametric equation, and symmetric equation, right?
Mm-hmm.
Any line will have three kind of equation: vector equation, right? And so let me tell you here. So let me recall you that if I give you a straight line, okay, and if I give you a point on it, let's say A, B, C. So let me put you here point, let's say x naught, y naught, g naught. Let's say you have a point on it and a vector parallel to this, let's say the vector having component A, B, C. Okay. Then the vector equation how given by vector equation? Vector equation is given by r vector equal to this x naught, y naught, g naught plus t into the direction vector A, B, C. Okay. And parametric,
Okay.
yeah, parametric equation how it given by? Parametric equation given by basically x equal to, yeah, x naught plus ta, y equal to y naught plus tb, and g equal to, yeah, g naught plus tc. Now symmetric equation how it given by? Symmetric equation, it is basically given by x minus x naught by a equal to y minus y naught by b equal to z. One second, one fraction will be there, so let me write it here. So in this place, uh, so here equal to g minus g naught by c. Okay, man, fine. So if you have a straight line, so let's say we have the straight line AB and we know a point on it, let's say x naught, y naught, g naught, and we know a vector parallel to it, let's say having component ABC. Then vector equation is given by x naught, y naught, g naught plus t into that vector. Parametric is given by x equal to x naught plus ta, y equal to y naught plus tb, g equal to g naught plus tc. Symmetric equation how it's given by x minus x naught by a, y minus y naught by b, g minus g naught by c. Okay, Mayan, clear?
Yeah.
Okay. Now in this case, for the normal vector, what is the point? Point is basically, see, a point on the, this is our normal line, right? This line is the normal line basically. So the point is basically P point having coordinate 1, -1, and 4. And the direction vector is what? That is the gradient vector, right? So gradient of f at the point 1, -1, 4. So this is nothing but the vector having component -4, 4, 8. So I'm writing the symmetric equation. Okay. So symmetric equation of tangent line is given by x minus this -1 divided by the first component, so -4, equal to y minus this -1 divided by second component 4 equal to g minus 4 divided by 8, like this. Okay. So if you want, you can rewrite x minus 1 by, you removing 4 from every term. So -1 equal to y plus 1 by 1 equal to g minus 4 by 2. Mayan, clear?
Yeah.
Okay. So what we have seen here, we have seen here the application of gradient vector, right? So the gradient vector for two variable, give you the normal vector to the tangent line, and gradient of for three variable will give you the normal vector of the tangent line at the corresponding point, right? Okay, Mayan. And we have
Okay.
seen, yeah, we have seen an example here. All right. I think this chapter is enough here. So I mean, it's okay for this chapter. There is no more in this chapter. I mean this section basically. The use of gradient in the context of tangent plane and normal line. Okay.
Mm, Sure.
I have sent the image. I also say share you this video also. I will upload in my YouTube channel. Okay. Okay. So I think we will stop here. Okay.
You sure? Okay.
Yeah. I stop here. So see you then in the next class. Okay. Bye.
Okay. Thank you. Bye.
Okay. Bye.